Today, we're diving into one of the biggest, most fundamental rules in the entire universe. And we're going to ask a simple question. Can it be broken? Right, we've all heard it a million times. Nothing, and I mean nothing, can travel faster than the speed of light. It's basically Physics 101, the ultimate cosmic speed limit. But what if it isn't? What if there's a loophole? A situation where it's possible to nudge just a little bit past that limit. Okay, so to really get why breaking this rule is such a huge deal, we've got to go back to the beginning. Well, the beginning of modern physics, anyway. We're talking about Albert Einstein and his special theory of relativity. And it's super clear on this. C, that's the speed of light in a vacuum. Is it? That's the absolute final maximum speed for everything. It's not just a suggestion, it's woven into the very fabric of space-time. But what if there's a tiny crack in that perfect foundation? What if deep down in the super weird, mind-bending world of quantum physics, there's a loophole? All right, now before you start packing your bags for Alpha Centauri, let's pump the brakes a little. The physicists who came up with this idea, they were the first to say, hey, this effect is, well, as Gabriel Barton from the University of Sussex put it, it's laughably small. So what is this loophole exactly? Well, it's got a name. The Scharnhorst effect. And the idea is pretty wild. It predicts that photons, the actual particles of light, can travel just a smidge faster than C, but only if they're in a very, very specific environment. The tiny, tiny gap between two perfectly parallel plates. And this special setup, that's called a Casimir vacuum. Okay, so how in the world could this even work? Well, let's think about something we see all the time. You know how a straw looks bent in a glass of water? That's because light slows down when it goes through the water. We can say water has a positive energy density. So the theory here is that this Casimir vacuum, the space between the plates, has the opposite, a negative energy density. Why? It's some pretty deep quantum stuff. But basically, the plates are so close together that they squeeze out some of the virtual particles that are constantly popping in and out of existence in empty space. And if positive energy density slows light down, well, you see where this is going. This negative energy density might just speed it up. And when we say a smidge faster, we are not kidding. We're talking impossibly small. For two plates just 1 micron apart, that's about the width of a single bacterium, the predicted speed boost is just 1 part in 10 to the 36th. That is a 1 with 36 zeros after it. It's so small, we can't even measure it. So yeah, the big takeaway here is this is super cool in theory, but we are not building a warp drive with this anytime soon. But this is where the story takes a sharp turn into sci-fi territory. See, even a tiny, purely theoretical violation of the speed of light, it throws a giant wrench into the laws of physics. And the biggest problem of all, it might just open a door to time travel. I mean, think about it. If you can send a signal faster than light, you completely mess with the order of things. You could, in theory, send a message back to yourself in the past. And that shatters one of the most fundamental rules we know, causality. The simple idea that cause has to come before effect. Physicists have a great little thought experiment to show how this works. It's called the tachyonic anti-telephone, which is a mouthful, I know, but it's a bit of a brain twister, so let's walk through it together. Step 1. You've got observer A, who sends a faster-than-light signal to observer B. Easy enough. Now, here's the kicker. Observer B is moving away from A and really, really fast. Because of Einstein's relativity, time actually ticks differently for them. So when B gets the message and instantly zaps back a faster-than-light reply, something really crazy happens. From A's perspective, because of that combination of super-fast signals and relative motion, they get the reply before they even sent the original message. And boom, there's your problem. You've just created what's called a closed causal loop. You could literally send a message back in time telling yourself, hey, don't send that message, which means you wouldn't get the reply to tell yourself not to send it. You get the idea. It's a paradox, and if there's one thing physics absolutely hates, it's a paradox. So, what gives? Is physics just fundamentally broken? Or is there a more clever, more elegant solution that saves the day and keeps the logical flow of time intact? Where causes still happen before effects.
Well, the proposed solution is really cool. It's not that causality gets thrown out the window. It's that the rules of causality might just be more flexible than we realized. Physicists suggest that even if you can go faster than light in these weird little pockets of spacetime, you still have to play by an even bigger set of cosmic rules.
Okay, to wrap your head around this solution, we need to talk about something called the causal cone. Just picture an event happening right now, like you snap your fingers. The causal cone is basically all the places in the future that your snap could ever possibly affect. The edge of that cone, the absolute limit, is drawn by the speed of light. And the number one rule is you can't get outside your own cone.
And this is where it all comes together, and it's a really brilliant idea. The solution isn't that you're breaking the speed limit, it's that inside that Casimir vacuum, the speed limit itself has changed. It's like the universe has created a new local speed limit that's a bit faster, so you get a new, wider causal cone. The photon might be going faster than the normal speed of light, see, but it's still playing by the rules. It's just riding along the edge of this new, expanded local light cone.
So, that's the key. The signal is still trapped inside its own set of local rules. Even with this new, wider cone, it has no way to jump out and zip back into the past. Causality is saved, the paradox vanishes. And it paints this incredible picture where the universe's speed limit isn't just one fixed number for everywhere, but a rule that can actually bend and change depending on your local environment. And this whole idea isn't just a one-off. The Scharnhorst effect isn't some lonely, weird theory. There are others. Take the Drummond-Hawthorne effect, for example. It basically predicts the same thing could happen, but in a totally different place, in the super-warped space-time right next to a black hole. And in both cases, you see the same theme, right? It's the environment itself, the weird quantum vacuum or the intense gravity, that's changing the local rules of the road. So that's where we'll leave it, with this really mind-bending question. If the universe's ultimate speed limit can actually bend, and if empty space isn't really empty at all, it kind of makes you wonder, right? What other fundamental rules of our reality are just waiting out there, waiting for us to find the right conditions to rewrite them?